So we have just finished test 2. I hope that wasn't too traumatic. I think the quiz was probably a lot more troubling, and I don't know what was going on with that thing. But I have a request in for Steve to look into it, and kind of hopefully that won't happen again. I think those quizzes are valuable. My intention for the quiz is to kind of get people to revisit some of the material, work out the cobwebs, work out any misconceptions, and get that cleared away before the test. And the way it went down, I'm not sure it had that effect, but I will be producing another one. So hopefully that was a kind of a long quiz. So we'll be breaking them up into smaller sections, so it won't be as many questions and stuff. So shorter quizzes more often is the idea going forward. And, yeah. Anyway, I will be kind of regrading some of those to see where people might have gone astray on that one question too, which had an error in it, but that is now that is behind us. So this week we're wrapping up chapter 5 by looking at 3D problems, equilibrium problems with rigid bodies. And just to maybe start off, this is where the supports get a little more complicated. When you actually look in 3 dimensions at how you support a structure, you can have relatively simple reactions. A cable, that's pretty straightforward. You find the direction of the cable, you know the direction of the force. So that's only one unknown. A smooth surface is only going to have a normal force perpendicular to the surface, right? A roller might have some side force to keep it from sliding more one way, but but typically what we're going to be looking at, we're going to have a lot of ball and socket joints. Those have 3 reaction forces. A pin was going to keep it from moving in 2 dimensions, X and Y. In 3, it would sort of also keep it rigid as well. A ball and socket allows the beam to kind of rotate in any direction, but not move out of the socket, right? The beam is stuck in that, it's captured in that socket, but it can rotate. When you get to things like journal bearings, these are the kind of things that machines will be using in a lot of cases. A journal bearing is something that it captures like a rod in a collar, and that collar is going to prevent the rod from moving, out of the collar, vertically or horizontally along the, transverse kind of direction of that collar. But it won't actually keep it from sliding through the collar. So there is no moment, there's no force in the Y direction that the thing can do as a reaction. Does that make sense? But there are also these moments too. It's not going to allow the rod to rotate out of the collar, right? It's going to be captured by that collar. So it's not going to allow rotation in the z-axis or the x-axis, right? So that means you get these potential reaction moments to these things, right? And also with more complicated ones, you can get a square journal bearing. That means it's not going to rotate as well along the y-axis, so you get an additional couple moments. This has an F. No, that's just a moment. That's not a force. It can still move along the direction of the collar. It just can't rotate. Then you would have there's a thing called a thrust bearing, which will prevent the rod from actually moving out of the bearing. So it captures the rod inside the bearing. So there is an Fy potentially that it can provide. Right, these are all the kind of reaction forces. So, and when we write the, oh, and also we're going to look at hinges. Hinges have these type of reactions. Again, a hinge allows a rotation around the y-axis, but it actually has basically 5 unknowns. It's going to keep that joint anchored in x, y, and z, both sides of it, and it's going to prevent a rotation around the z and x axes. So yeah, anyway, so it gets kind of complex, and we're going to be looking at those different things today. Here is a real machine, you know, that's kind of a pin there. So if support prevents rotation of a body about an axis, then that support exerts a what about the axis? A couple moment. Yeah, if it's preventing rotation about some axis, it has to provide a couple moment to keep some of the moments equal to 0. If there's an applied rotation on it, it's going to fight that by creating a counter moment to keep the thing from moving. And then when doing a 3D problem analysis, you have blank scalar equations of equilibrium. 6, because you can have 3 equations of forces in the x, y, and z, and 3 equations of moments in the x, y, z. So that means the problems become a lot more complicated. Extra handouts for Connie, are they out there? Okay, thank you. And yeah, so you can do some of the forces in the x and some of the moments in the x, y, z. Fortunately, the equations are usually fairly simple, and often we don't get 6 equations because of the way the supports are oriented. Again, here are some of the ones we just looked at: a roller, ball and socket, fixed support. Fixed support is where you got something just buried in cement, not going to allow motion in any direction. So 6 unknowns there. You can see some examples of real supports, ball and socket, right? What's this thing? Some kind of bearing, could be a journal or a truss bearing. This is kind of a pin. This would be what? At A. Fixed support. Yeah, the wing is just fastened straight to that fuselage. There is also a commonly understood way of mounting various things so that you don't have all of the reactions needed, right? So has anyone ever seen a door hinge mounted in the middle and not having any other hinges in the door? That would be a pretty bad idea, right? You think the door would stay in its place if you did that? Probably not. The reason why that's a bad idea is the weight of the door provides a moment, you know, about this point right here, right? You have the moment is W times D. So the moment about that hinge, just from the weight of the door alone, is going to be W times D. And it's going that way. So if that door is not going to move, which we don't want it to, it's just hanging open like that, then the hinge itself has to provide a counter moment, right? And how that counter moment happens, it's a little bit hard to kind of visualize, but you know how hinges work, they kind of have these plates. I don't know if that works. That's see how good my art skills are. These plates here, which has, you know, these screws, right? And then the other side of the hinge is interlocking there, and there's a pin in there, right? So if that hinge is going to provide a moment, what's going to happen is there's going to be kind of a sense of the interlock portion from the other side of the hinge, you know, trying to rotate out of that thing, and the pin is going to have to kind of push back with like a force that way and a force that way on that side to keep that thing from rotating, right? And that's going to really jam up that hinge pretty bad, right? So the hinge isn't going to actually work too well. You should put that kind of stress on it. So instead, what we do is we put at least 2 hinges on a door, and we separate them by a certain distance. And now those hinges, even though they can provide reaction moments to keep the door from moving, they don't have to anymore, because the sheer separation of the hinges by this distance d prime means that they only have to, they can actually provide a counter moment, right, from this, the weight of the door about the axis of the hinge. They can provide a counter moment by providing a fx that's separated by d prime. And now fx is going to be a lot smaller than w, because the distance of separation of those hinges is a lot smaller than the distance from the center of mass of the door to the line of the hinges, right? And they're actually just providing a single force in one direction, so it's not actually twisting the pin of the hinge. Any questions on that? That's kind of a weird thing, but basically what that means is, even though hinges can have something like, 5 reactions, in this case, the hinge is only going to need to provide like a by and an ay, and then this fx, fy counter moment. So that's a lot less unknowns. This also happens with journal bearings as well. We'll see some example problems where that. So here is a simple situation, and this is on your handout, right? Good. Writing the free body diagrams is, again, the first part of solving these problems. Here we have a hanging flower pot off of a boom with some cables attached to it. We want to actually draw the free body diagram of that boom with all of the reaction forces and all the forces acting on it, right? So maybe that boom has a weight. We're not given any, so we can call it, I don't know, weight S. What is S? Well, let's call it weight of the boom. If there is one, we could put that right in the middle. And then what kind of support is here acting at O? That's a ball and socket. And what were the reactions? Anyone remember? Yeah, there's an FZ, oops, FZ, an FY, and an FX. And we can maybe do it this way. Actually, we might call this, instead of F, since there's going to be a lot of F's here, sorry about that. We might call it like O, O, Z, O, X, and O, Y. And then, you got these cables here, cable going from A to C. So naturally, we would have like a TAC, a vector, which is going to have, we know the direction, we just don't know the magnitude of that. Same thing for TAB. And then also the weight of the pot. So if we're given like the weight of the boom and the weight of the pot, there's only 5 unknowns. We can solve this with the 6 equations of equilibrium. We only need to write 5 equations and solve it. Alex?
Can you talk about the forces on B and C?
The forces on B and C, do we need to worry about those because they look like fixed supports? Yeah, it's interesting here, but the forces on B and C are really just the opposite of the TAB and TAC, right? So they don't actually give us any new, unknowns that we need to worry about, right? Yeah, they are sort of fixed supports, but if this was something that we needed to analyze separately, like the forces on the wall or something, we might need to do that. But they don't really come into play with any new information that we need to worry about. So we don't bother putting them. Remember, the free body diagram is you're sort of finding the key piece of the puzzle that you remove from the whole system and just put the forces acting on that. So we don't include anything that's not part of that beam, that's not directly attached to that beam. We just ignore. And that really helps us clarify the problem, right? Because once you pull that beam out and just look at it, it's a lot easier to say, oh yeah, there's just these 5 forces we got to deal with, right? And usually it's obvious what the thing is that you're doing the free body diagram on, right? We're going to do the free body diagram on this pipe thing. These pipe problems are a little strange. You'll find all kinds of weird pipe arrangements that they can kind of create for you. And it's really just a chance for us to kind of try out these different reaction forces, support reactions. And that doesn't really look good. Let me get rid of that line. So this guy, the first step is we're going to draw this thing. As best as you can, with whatever artistic ability you bring to the problem. And, we can start with the known forces acting on it. We've got this 300-pound weight acting on the elbow there. What's going on right here, though? What is this? Yeah, it's a couple moment acting on that beam. What's it doing? Trying to make that whole pipe kind of rotate, right? It's like we're trying to rotate that thing. And it is a couple moment. It's not a force, right? So we draw it with the arrow and the circle, and we put 200 pound-feet. So if you can imagine, you're gripping that thing, that part of the pipe with your hand, and you're trying to twist it, without moving it. You're just trying to make it twist, like you're wringing it out or something. That's what that couple moment is doing. So then we've got, this tension force at BC. That's going to be one unknown. And then we got to figure out what's going on at A. Okay, a lot of these things, you can just kind of intuit what the reactions are just looking at the support. This is this would be an example of, it's not really a journal bearing, but it's kind of like one. I think you can kind of see it's capturing that thing, so it's going to provide reactions in different directions. And let's sort of think about what the directions are that this thing is going to prevent motion on, right? Could this pipe here lift up from A? Would that be allowed? Would that thing let it happen? No. So there is a reaction there. So we can call that an AY. Now we're drawing it up. Don't worry about the direction. We don't really know if it's going to be up or down, or maybe it's even going to be 0. We don't know. Some of these things, they're not going to be needed. Not clear that all these reactions are going to be needed, but these are potential reactions that the support can provide, and we have to actually analyze it to see if they are going to be needed. Could the pipe move this way out of that thing at A? No, so there's going to be an AX as well, right? Let's define our axes. There isn't one given to us, so we can make it any way we want. I called that AY because that was what looks like here. It looks like, just for our sanity's sake, we're going to have a Y going that way. We're going to have X going this way and Z going that way. It's still a right-hand system, right? X cross Y is Z, but it's sort of tipped in an odd direction. So AY is going to be going up, and this thing that's preventing motion, what I thought was X, is actually going to be Z. So there's going to be an AZ there, right? So you can have an AZ here, and you can maybe draw a big fat arrow in there. That's going to be AZ. And is it going to allow motion in this direction? Could that pipe kind of slide in that direction? No, so we'll have to put an RAX, or not an RA, just what's called an AX in that direction, right? Could potentially have that needed there, but we don't know yet. What about moments? What reaction moments might that thing apply? Can anyone see what axis might there be a reaction moment about? Y. Good. Yeah, it's not going to allow it to rotate about the y-axis, right? That would mean it would have to kind of rotate that way, right? It's not going to allow that. So we'll have a reaction moment, and we can call it MAY. It's also not going to allow a rotation about the z-axis, right? So we're going to have an MAZ. And do you notice the sense that we're doing it? We're doing it with our thumb going in that direction of the axis, right? If we want to find the sense of MAZ, our thumb would be going, point your thumb along the z-axis, and in the direction that your fingers are rotating are the directions that we're going to make the arrows go, the circular curlicue go for the moment. Does that make sense? So we're just assuming that's a positive moment, right? It's a positive moment directed around the z-axis or the y-axis. And we can also probably see that there isn't going to be one about the x-axis because of the way that bearing is. It looks like it's going to allow that thing to kind of rotate about the x-axis, right? So how many unknowns do we have? 1, 2, 3, 4, 5, 6. 6 unknowns. We can solve this thing with 6 equations. We'd have to write 6 equations to solve it, but we can do that. Okay, questions? Another one is this board here. Again, who would ever make something like that? I don't know. It's an art project. So what's the body of interest? Well, it's this platform, right? We have to do all the forces acting on that piece of wood. You've got a hinge, a journal bearing. Now it says it's properly aligned, and properly aligned means, when you see that, that means that it's not going to need any extra moments to kind of make it stable. We generally want to make our journal bearings properly aligned so they don't have to do crazy moments. I mean, sometimes they might. If it doesn't say it's properly aligned, you might want to look into that. But that means you don't have to worry about those moments that might be needed in other situations. So we're going to have, you know, the 400-pound force acting here. We're going to have, again, for some reason, my axes are in the same kind of tipped over form. So Y, X, and Z. There's no reason why you can't make it in a more favorable, if you like it with a Z going up, you can do that as well. But stick with your axis and then, you know, be consistent. So at B, this is a roller. So what kind of reaction we're going to have at B? Just a vertical force, right? We'll call that By. The hinge at C, if it's properly aligned, right, then that hinge isn't going to need much either. The only thing that hinge is going to do is going to be what? Sorry? X, Y, Z. Yeah, it's going to keep that point at C kind of anchored, right? It's not going to allow that point at C to move up, down, left, or right, right? The hinge is capturing that point there, kind of like a ball and socket. So we're going to have a CY, a CX, and a CZ there. Again, if it's properly aligned, you know, then we don't have to worry about it doing any weird moments about the y-axis or the z-axis, right? It's just needing the forces there to keep the thing. So this allows us to solve it. Oh, at A, we're going to have this property line journal bearing. Again, that's going to anchor it in terms of the vertical and horizontal directions, Y and Z. So we're going to have an AY and AZ there. 1, 2, 3, 4, 5, 6, 6 unknowns. We could solve it. If it wasn't properly aligned, then you have extra reaction forces, and you wouldn't really be able to solve this thing. So the rod AB supported using 2 cables at B and a ball and socket at A. How many unknown support reactions exist in this problem? Ball and socket, how many reactions? And 2 cables, how many reactions? Okay, so 5 forces, right? Good. Okay. Another problem. More free body diagram examples. We're going to do a couple, I think, actual problems to solve. Tomorrow. So we're going to go back and look at example 4. So this other example. You know, again, you've got, you know, a ball and socket. You know, actually, it gets a little redundant. If we assume, let's just look at the journal bearing here, though, because everything else is pretty obvious. The journal bearing is going to have, again, it's going to have an A. Our axes are this way, so our axes are going to be Z, X, and Y the traditional way. So we're going to have an AZ. Actually, they're giving us the origin right there, so we don't have to do that. So we're going to have an AZ there. We're going to have an AY. And it's bearing, so we're going to sort of assume that it is a properly aligned journal bearing. So it just needs an AX and an AY, right? You're going to also have 3 reactions here and 1 reaction there. Going to give you a total of 6 unknowns. Okay, just throw some arrows on there. You can come back to that later if you didn't get all that. We're going to finally do this one start to finish. So this one is well, what we're going to do is determine the reaction forces at A and the tension in the cable. Is this on your handout where we have all those things labeled already? Not skip a page. It is. So yeah, in the interest of time, let's just you can draw that free body diagram and kind of work all that out, but it's the same thing as this guy right And we went through all the trouble and labeled all those points. And now we want to find the reaction forces at A and the tension in the cable. Now this is if you look carefully at this thing, this is a square collar bracket thing. So that's going to give us it's going to give us, it's going to give us reaction moments, reaction forces. This is RAX, these are forces AX, AY, and it's going to give us moments. So 2 forces, 3 moments, and 1 force TBC there. So that's, again, 6 unknowns. And F is 120 newtons, and it is in the minus K direction. Okay, so we have to find. Yeah, I usually would just write, instead of RAY, I would just call that AY. Does that make sense? I just like AY, AX, just less clutter. It's a reaction, so that's why in this handout it says R. But I think it's obvious that these are reactions, so you have to put R's in front of them. You're welcome to if you like. So we have to find AY. We have to find AX. We have to find MAX and MAY and MAZ. And we have to find TBC, the magnitude of that. So that's a lot of work to do. These problems take more time. There's fewer problems on the homework set this week because of that. So again, we're saying F equals minus 120 newtons in the K direction. So, and then we're going to also have to figure out, the whole position vector thing for TBC, right? That's pretty time consuming. But let's just kind of crank it out here. So TBC, if you've got those 2 points located, it's going to be the unknown magnitude times the unit vector in the BC direction. And that's TBC times, and we're going to have UBC. Well, we got to go minus 12 in the X direction, so minus 12I. We got to go 4 in the Y direction, going from 4 to 8, so plus 4J. And we got to go 6 in the Y direction, plus 6K. All over the square root of the square of those things, just add it together. So that's going to give us a vector that has a magnitude of TBC and a direction of minus 6/7 I plus 2/7 J plus 3/7 K. So that's just one unknown. So the sum of the forces equals 0. Well, you've got to add those 3 things together. Now you can do the sum of the fx's, the sum of the fy's, and the sum of the fz's. Or if it's not too complicated, you can do them as vectors, right? So you can do the sum of all the A forces plus the sum of all, well, plus the sum of that, plus that F force that's given to us, plus the TBC force has to equal 0. So you can list them all as vector components. I usually don't do this. I usually just say, let's do the sum of the fx's, sum of the fy's, sum of the fz's. But it's one way if you like to do it in sort of vector notation. It can be a little briefer, maybe, I don't know. If you do it this way, you're going to have ax times I plus ay times j plus az times k. There's no az, so don't write that. And then there's this minus 120k for f. And then there's going to be minus 6/7 TBCI plus 2/7 TBCJ plus 3/7 TBCK. So you can actually tally things up, right? Along the I direction, you can see that AX minus, well, AX has to equal 6/7 TBC. In the J direction, you can see that AY has to equal minus 3/7 TBC. And in the K direction, you can see that 120 newtons has to equal 3/7 TBC. Wait, did I miss something? Oh, I have an error here. It should be, the AY should be minus 2/7. And therefore, TBC equals 280 newtons. And we can move up. Now that we know TBC, then we know that AY has to equal minus 80 newtons. And finally, AX has to equal 420 newtons. So that's the three unknown forces, but then we still have these three reaction moments to figure out what's going on with that square collar bracket thing at A. There's three unknown moments still we have to figure out. And again, you can use vector formulations, or you can use scalar moments if you like, but we're going to do vectors. So so we can pick some point on here. You know, you might be tempted to do the sum of the moments at A. But if you do that, you're going to have to do a whole bunch of, well, you have to do this big cross product of TBC, you know, crossed with, you know, R cross F. You have to do RAB cross TBC. If you do the sum of the moments at B, that might be a little bit easier. It should work the same either way. Let's just do the sum of the moments at B. And in this case, if we do it at B, we're going to label moment arms here. So if we can do the moments at B, we're going to have to label this moment arm here to go from B to A, so this is going to be RBA. And we're going to have to label this moment arm here as RB, we'll call that BF. So it's going to equal, we have to do RBF crossed with F plus RBA crossed with all of our A forces plus our reaction moments, all of our reaction moments at A. These are not fun. Well, they can be fun, but they're involved, right? So you have to be really careful and grind through this stuff and just really check to make sure you don't have like some screwball sign error or something like that, right? There is a common sense thing you can kind of apply at the end as well. So 0 equals, and RBF cross F is going to be minus 4J crossed with minus 120K. And then to that, we're going to do RBA cross RA. And RBA is going to be minus 12 in X so that's minus 12I, and minus 4 in Y, minus 4J. Again, we're going from B to A, right? Everyone see that? And we're going to cross that with our components from the previous. We have to cross that with our reaction forces AX and AY. And AX is 420, AY is minus 80. So that's going to be 420I minus 80J. Okay, what else do we got to add to this equation? Sorry? So all the moments at A, right? So then we got to add to that plus our reaction moment along the A-axis times I plus our reaction moment along Y-axis times J plus the reaction moment Z-axis times K. Those three unknowns that we're trying to figure out. So that's going to equal 480. So that's minus 4J cross minus 20K. So again, J cross K is I, right? And minus 4 times minus 120 is 480. That's going to be 480I plus 960 that is going to be, what is that? What is 960? Is that what is 960? 12 times 80? 12 times 80. So that's I cross J, which is K. So that's going to give us 960K. We also have to do 4 cross, so J cross I. So J cross I, 4 times, that's going to give us 1680K. Plus MAXI plus MAYJ plus MAZK. And that pretty much just puts the answer right out in front of us. So that means that MAX has to be minus 480, and that is pound-feet. MAY is 0, it's not needed. There's no J term in there. And MAZ is going to equal the sum of those two, minus 2640 pound-feet. Get up and take a break and walk around because they're pretty intense, right? You got to focus pretty hard, pretty long, and get through all this stuff. Now the last problem, we're a little bit running low on time. I think it'd probably be helpful to kind of crank through it. Again, there is a lot of stuff here. So if you can stick around, that would be great. If you need to leave, that's fine. Why don't we do the attention quiz, see if this makes any sense. A plate is supported by a ball and socket joint at A, a roller at B, and a cable at C. How many unknown support reactions are there in this problem? You've got a ball and socket at A, right? So that's going to give you 3 forces. You've got a roller joint at B, that's going to give you 1 force, and a cable at C, which is going to give you 1 force. So the answer is 5 forces. Good. What will be the easiest way to determine the force reaction BZ? This is actually a nice thing to do. To find BZ, what would be the easiest way to find BC? So the moments at A. If you do the sum of the moments at A, you're going to have to deal with, BZ, the 400 Newton force, the cable, and the 300 Newton force. A lot of terms there. Is there a simpler way? Sorry? C. The scalar equation, sum of the moments about the z-axis equals 0. Is that one? BZ is not going to give a moment about the z-axis, though, because it's parallel. D. The scalar equation, sum of the moments about the y-axis equals 0. This is actually the beauty. So you can do all these vector things. You can do the vector cross products and all that stuff. That's a way to do it if you're not comfortable with what's going on here. But if you can see this, right? If you can see the moment about the y-axis, check this out, right? If the moment about the y-axis means, well, you can ignore this because that's right on the y-axis. You can ignore this, that's right on the y-axis. You can ignore all these forces, that's all on the y-axis, right? The only thing that's going to give you a moment about the y-axis is going to be BZ and the 400 Newton force. So all that vector stuff, I don't know if I should keep showing that. It's really helpful to, I think, to kind of see how vectors actually work. But if you can do these scalar moments, it's so much easier, right? So it's just going to be, BZ, well, BZ times 4 minus, because we're kind of going, if your fingers follow along, your thumb's going backwards along the y-axis, plus 400 times 2 equals 0. So then BZ is just, what, 800 over 4. It's just 200. And it makes perfect sense, right? As you start visualizing the problems this way, they become a lot less intimidating, right? Obviously, right, this has to be 200 because you got a 400 Newton force here that's 2 meters away. It's causing a sense of rotation about there, right? And to stop that, you're going to have half the force at twice the distance because the moment arm is double, right? So this is the kind of thing where intuition starts to kind of help out when you solve these. So if you want to stick around, we can do this one. And instead of all that vector approach, I mean, we still have to do the vectors for TAB and TAC. That's really kind of a challenge. But when we do the moments, you can do them with scalar moments. So just to kind of speed up the chase, you can get to the point where TAB is going to be it's going to be 2/7. It's going to be the unknown magnitude, right? TAB times 2/7 I plus 3/7 K. Maybe I should just do this. You guys have to go. You guys good? Want to stick around? We're going to be doing this in class tomorrow, so I'll be kind of guiding you through this as well. Please make sure you show up. It's a really important practice session to kind of get exposed to. And then TAC is going to be the magnitude TAC. And again, you've got a minus 2/7. That's an I, minus 6/7 J, and plus 3/7 K. And then you've got this OZ, OX, and OY, and you've got all those moments, right? So with the moments, you can find, say, the sum of the moments about the x-axis equals 0. Let's look at that. Do the sum of the moments about the x-axis equal to 0. What happens is, what's going to give us a moment about the x-axis? Well, we're going to get w times 6, right? And if we're doing the moments about the x-axis, at O, right? So we're doing the moment right around that x-axis, right? So that w times 6, is that going to be positive or negative? It's negative, following the right-hand rule, right? Because your fingers kind of curl around and your thumb is pointing against the next direction of the x-axis, so it's going to be minus w times 6. And what else do we got here? Well, we got the vertical part of TAB is going to give us, right? And then what else in TAB? Is the y component of TAB, is that going to give us a moment about the x-axis? Is the x component of TAB going to give us a moment about the x-axis? Now, we only really need to focus on the y component of TAB and TAC, right? Those are the only things that are going to give us a moment about the x-axis. You see that? You can see that that's good. If you can't, then you got to do that vector analysis. The vector analysis, I think, is kind of really good for people who can't visualize these sort of 3D rotations and stuff. But the scalar is really helpful if you can. It makes your life so much easier, right? Because it's going to be plus TAB times, let's see, the vertical component is going to be times 3/7, and the moment arm is going to be 6, right? Actually, yeah, no, that's good. And then plus TAC times the same deal, right? Times 3/7 times 6 as well. That has to equal 0. And the weight is 30, so that'll basically allow us to have at least one equation, 2 unknowns. Right? Some of the moments about the, plus actually though, there could be, no, that's actually just a, yeah, there isn't going to be any moment there from that support, right? But also now the sum of the moments about the y-axis equals 0, and about the y-axis, Well, there isn't anything, right? So there isn't really any moments about the y-axis. Okay, that already is true. And the sum of the moments about the z-axis equals 0 is going to give us, again, just the horizontal component of TAC, and that's it, is going to give us a moment about the z-axis. So that's just a way of sort of looking at these things. And so you could have, TAB times 2/7. And, that moment arm is going to be 6 again. And that's going to give us a negative moment about the z-axis, and then a TAC times minus 2/7 times 6. But actually, we kind of don't worry about the signs. This can get a little confusing. So then that basically is going to be plus. And so that's going to equal 0, and that's going to tell us that TAB equals TAC. And that means that we can then sort of solve for these, because those are the same. Then basically, they each are going to be equal to 35 pounds. So you find TAB, you find TAC, and then the those total forces, we have to take into account whatever that ball and socket has to do. We can do the sum of the FX's, the sum of the to find whatever that ball and socket has to do, right? So the sum of the FX's equals 0. That's going to equal, it's going to be equal ROX. And it's going to equal plus TAB times, what was that, 2/7, and minus TAB times 2/7. Again, that means, well, those things are already the same, so that means ROX equals 0. And the sum of the FYs equals 0. Do I have any room there? I'm running out of room. The sum of the FYs equals 0 is also going to show that the ROYs is going to equal, actually there's going to be a leftover for the ROYs, so the Y forces are going in there, right? Yeah, because these are both sort of pushing in, right? So the ROY is going to have to push out to counter that thing. So that's going to equal, minus 6/7 TAB, minus 6/7 TAC, and then plus ROY. And solving all that would tell you that ROY equals 60. And finally, ROZ, if we sum all of the Z forces, I think there is no, is that right? There's no need for a Z force, because those cables are actually supporting that weight right there at the end. But you can find that out as well if you do the sum of the Z forces. You'll find that out. So they're fun. They are challenging. You sometimes can go down, you can make false starts, and you have to kind of circle back and kind of try a different approach sometimes, because you got a lot of equations. And there's generally, once you get good at it, there's generally like a relatively straightforward way of picking your way through all the unknowns to find the ones that you can get. You kind of go for the low-hanging fruit first, and then you use those to find the other ones. And we'll do those in class tomorrow, so I hope you'll all be there. Thank you for staying.